So, we have seen the impedance matching using a series stub. Let us now consider another type of stub matching, the impedance matching with a shunt stub. We first derive the analytical expressions and then we will solve an example problem of shunt stub matching using Smith chart. So, we start with an impedance ZL. Now, this ZL is to be matched to a transmission line having characteristic impedance Z0 using a shunt stub. So, first of all, what we do? We find out a distance d from the load impedance ZL, where if we look, we find y in at this point becomes equal to y naught, that means 1 by z naught, and it will have a susceptance component J B. Now, so the distance of the stub location d is so chosen that y n becomes equal to y naught plus J B. Now, once we do that, next we put a stub of length L, and it may be an open or a short stub, and the length L is selected in such a way that if we look from this point into the stub, we get minus J B. So, the stub length L is chosen for a short or open stub that input susceptance of the stub is minus J B, and this plus J B minus J B will get cancelled, and that will result into matching. So, we know that Z in is given by Z naught, ZL plus Z naught tan beta d divided by Z naught plus JZL tan beta d, and with this we develop the analytical solution. So, we can write y n equal to 1 by Z in, and which will be G plus J B. We have already stated that we choose this d in such a way that this G becomes equal to y naught. That means, we equate the real part of y n equal to G to y naught and find the solution for d. Then once we have the computed value of d, with this we find out b, and then the stub length L is found for a short or open stub to provide minus J B. So, as in the case of series stub matching, let us replace this tan beta d by t. Then this equation Z in can be put in this form, tan beta d replaced with t, and then we can group the real and imaginary terms, and we get this resulting expression. Z in is equal to Z naught R L plus J X L plus Z naught T divided by Z naught minus X L T plus J R L T. Now, y in is G plus J B is equal to 1 by Z in. So, from this expression we can calculate the expressions for G and B. So, that we can do by multiplying the numerator and denominator by the conjugate of this term, then this will become actually, once we multiply this with this conjugate, it will become real, and then we group again real and imaginary part, and in that way we can find the expression for G and B. Now, we start with the expression for G, and once we equate it to y naught, then we can solve for t by forming this quadratic equation. So, here you put G is equal to y naught equal to 1 by Z naught, and then rearrange the terms, then we will get this quadratic equation. Now, here you note that if RL is equal to Z naught, then this term becomes 0. That means, the real part of the load impedance, if it is same as characteristic impedance of the line to which it is to be matched, then we get a very simple solution for T, which is minus XL by 2 Z naught, because this RL Z naught will get cancelled with RL square. So, we will be essentially having minus XL square divided by 2 XL Z naught, and this will give us T equal to XL by 2 Z naught. But if RL is not equal to Z naught, then T is equal to XL plus minus root RL Z0 minus RL square plus XL square, whole thing divided by Z naught, and in the denominator we have RL minus Z naught. So, since the equation in T is a quadratic equation, we will get two values of T, two solutions for T, and correspondingly we will get two solutions for D. We write d by lambda is equal to 1 by 2 pi tan inverse T when T is greater than 0. This comes directly from T is equal to tan beta D, and beta is 2 pi by lambda. So, when T is less than 0, to get a positive length D, we solve 1 by 2 pi plus tan inverse T to be equal to d by lambda. And once the values of T are calculated, we can calculate the value of B by substituting the value of T in the expression for B. Since we are having two solutions for T, we will also get two solutions for B, and the necessary Stub susceptance Bs is equal to minus B. Let us denote the length of the open and short circuited stubs by LO and LS. Then we can find out LO by lambda is equal to 1 by 2 pi tan inverse Bs by Y naught, and this can be written equal to minus 1 by 2 pi tan inverse B by Y naught. And similarly, for the open circuited stub, Ls by lambda is equal to minus 1 by 2 pi tan inverse Y naught by Bs, which can be written as 1 by 2 pi tan inverse Y naught by B. So, we have found out the solution for D, the location of the stub from the load impedance, and also we have found out the expression for the length of the stub, and depending upon whether an open circuited stub or a short circuited stub is being used, we can calculate their lengths. It may be noted that if this length while computing comes out to be negative, then we add lambda by 2. Now, we take the example of an impedance matching using shunt stub. So, let the load impedance to be matched is given by ZL is equal to 100 plus J 60 ohm, and this is to be matched to a 50 ohm line. So, by applying the analytical solutions, we get a value of T to be equal to 3.4091, which we call T1, and another value of T is minus 1.0091, which we call T2, and we get two solutions for D. In fact, d1 by lambda comes out to be 0.2046 and d2 by lambda, this is 0.3743. Similarly, we get two solutions for B. B1 is 0.0221 and B2 is minus 0.0221. Now, with these values, we can now calculate length of the open circuited stub. So, two solutions are again possible. So, LO1 by lambda is 0.3671 and this one, if you consider other value B2, this tan inverse will come out to be negative. So, we have to add lambda by 2. Here you note that LO2 by lambda we are calculating. So, this becomes 0.5 plus 1 by 2 pi tan inverse B2 by Y naught, which comes out to be 0.1329. Now, these are the two locations of the stubs and the corresponding open circuited stub length can be used to complete the design. Next, what we do? We verify our analytical design by comparing with Smith chart solution. So, our load impedance ZL is 100 plus J60, which can be shown by the normalized impedance of 2 plus J12 in the Smith chart. Next, we draw the constant VSWR circle, pass this line through the center of the Smith chart, and then we find out YL, the admittance, normalized admittance. Next, what we do? We use this Smith chart as an admittance chart, and as we move from this towards the 1 plus JB circle, we intersect first at this point, which is 1 plus J11 1.1, and we draw a line from the center of the Smith chart through this point. Similarly, if we continue over the VSWR circle, we intersect 1 plus JB circle for the second time at this point, and we find that here the value is 1 minus J 1.1. We draw another line through this point from the center of the Smith chart. Now, we calculate the distances d1. We can see that so we find from the Smith chart that d1 by lambda is equal to 0.204 and d2 by lambda is equal to 0.376, and corresponding lengths of the open circuited stub can be found out. LO1 by lambda is equal to 0.368 and LO2 by lambda is equal to 0.132. From the analytical solution, we got T1 is equal to 0.34091, T2 is equal to minus 1.0091, D1 by lambda 0.20459, D2 by lambda 0.37428 and L1 by lambda is equal to 0.36710, L2 by lambda is 0.13290. So, we can see that the solution for D1, D2 and LO1, LO2 obtained graphically from the Smith chart is quite close to the solution that are obtained analytically. So, we have seen how we can do impedance matching using single stubs, either series or shunt stub. Now, these stubs can be fabricated along with the transmission line, particularly when we use planar transmission lines, the stubs can be fabricated along with the lines. Generally, shunt stubs, these are preferred for microstrip or strip line type of transmission line, whereas series stub is preferred for slot line or coplanar waveguide type of transmission line. Again, as far as fabrication is concerned, when it is a planar transmission line like microstrip line, open circuited stubs are advantageous because we need not use any via connecting the strip conductor to the ground plane, whereas short circuited stubs are preferred when we consider coaxial type line. Let us now move on to another type of stub matching where we use more than one stub. So, let us see how we can do impedance matching with double stub. Now, these two stubs may be spaced at a fixed distance and also located at a fixed distance from the load. So, here we consider the load represented by YL dash, and these are the two stubs which are located from a fixed distance from the load. They are separated by a distance d and the stubs have lengths L1 and L2. The stubs may be open or short. Now, what we do? First of all, this YL dash, it is transformed by this length of the transmission line, and now it is YL is the load that is seen at the location of the first stub. So, load YL dash is transformed to the position of the first stub as YL. Now, what we need to determine again the values of D, L1 and L2 depending upon the type of the stub that is being used. So, we can write Y1, that is admittance at the location of the first stub, YL plus J B1, which can be written in this form, GL plus J BL plus B1, and then once we transform this Y1 to the location of the second stub Y2, then we get Y2 is equal to Y naught Y1 plus J Y naught tan beta D divided by Y naught plus J Y1 tan beta D, and then for matching we need real part of Y2 to be equal to Y naught, and once we do that we also get a solution for this distance D. So, similar to our earlier cases, let us put T equal to tan beta D, then substituting tan beta D by T here and substituting Y1, we can write Y2 in this form, and after the rearrangement of terms, y2 can be put in this form: GL plus J BL plus B1 plus Y naught T divided by Y naught minus BLT minus B1T plus J GLT, and this entire term multiplied by Y naught. Now we equate real part of Y2 with Y naught, and then we get a equation of this form. This is a quadratic equation. We can find out GL, and what we find that GL is real. Therefore, this term, please notice both numerator and denominator, they are positive values because of these squares, and therefore, if we want to get this GL to be real, this entire term has to be less than 1. So, this becomes greater than 0 and less than 1, this particular term 4t square y naught minus BLT minus B1t square divided by y square into 1 plus t square whole square. So, this term is greater than 0 and less than 1, and this will only give us a real solution for GL. And from this equation, now we can write GL is between 0 to y naught by sin square beta d. Similarly, we can find out the expression for B1 and B2, and once we calculate B1 and B2, we can calculate the lengths of the open and short stub by these relationships, where this B is either B1 or B2, and therefore, we get the location which is fixed already D, the separation for that particular location. Now, we get the solution for the short and open circuited stubs, their lengths in terms of lambda. We have seen the double stub matching analytically, and we have derived the closed form expression for computation of stub lengths. Let us now consider double stub matching using Smith chart. As shown in the figure, YL is the load admittance which has been transformed to the location of the first stub, and the two stubs are connected, separated by a distance d. We have the reference locations A dash and B dash at the location of the two stubs. Now, if we look at this double stub matching circuit, we find that Y I, the input admittance, is equal to Y B, the admittance looking from here, plus Y S B, the admittance of the stub. The stubs may be open or short as shown. Here we need to find out the lengths of the stub L A and L B. We can write this equation in the normalized form: 1 is equal to normalized Y B plus normalized Y S B. Since Y S B is purely imaginary, this Y S B is purely imaginary, and we must have YSB equal to minus JBB, the susceptance of the stub, so that we finally get yi equal to 1. And therefore, we find that in Smith chart yb must lie in the g is equal to 1 circle. We are using the Smith chart as a admittance Smith chart, and since the real part of yb is 1, it must lie on the g equal to 1 circle. To meet this requirement, ya at a dash must lie on the g is equal to 1 circle rotated by 4 pi d by lambda counterclockwise, that means towards the load, because then only once we come back to g is equal to 1 circle, we will get the required value of yb. Since YSA, the stub admittance, is purely imaginary, the real part of Ya must be contributed solely by the real part of YL, and real part of YL is GL, and therefore, the solution of double stub matching is then determined by the intersection of GL circle with rotated g is equal to 1 circle. So, let us explain this on a Smith chart. So, we follow the procedure as shown. We plot g is equal to 1 circle and yb should be located on this circle, because after matching we require yi equal to 1. Plot the rotated circle where ya should be located. Now, this rotated circle, we have seen that it is to be rotated counterclockwise by 4 pi d by lambda. Here we are considering an example where d is equal to lambda by 8. Therefore, this circle has been rotated by pi by 2. Next, what we do? We plot YL. So, this is the YL point shown. Now, as we have said that the G is same as GL on this particular circle, when we find Ya, the real part of Ya should be equal to GL. So, what we do? We move across this constant G circle which is equal to GL and find the intersection point, first intersection point here, and this is Ya 1. Please note that real part of this Ya 1 is same as GL, and then as you continue moving, we get over this circle, we get another intersection point Ya 2. Again the real part of this is same as GL. Now, these are the location of Ya on the rotated g is equal to 1 circle. Now, this has to be transformed to g equal to 1 circle to get the corresponding yb points, and in order to do that, we now move by the distance lambda by 8 or an angular movement of 4 pi lambda by d, that means here in this case pi by 2, and follow a VSWR circle, so that we find out the intersection Ya 1 on the rotated g equal to 1 circle actually corresponds to this point Yb 1 on the g equal to 1 circle. Similarly, we find that this point will be transformed to this point, which is shown as YB. Now, we have all the 4 points located. So, we can see that at this point YB1 is having a value 1 plus JB in that form, and we can find out the corresponding stub length that will compensate for the imaginary part. Similarly, here at YA1 point, we have the real part to be GL and the imaginary part has a value. So, this starting from this point, this additional susceptance when added will transform YL to YA1 values, and we can calculate the length of the stub that would be necessary for this additional susceptance. So, we can calculate for the other 2 points YA2 and YB2 as well. So, we can determine the stub lengths LA and LB that would be necessary, and the lengths will depend on whether we are choosing open circuited stub or short circuited stub. So, this is how we can use double stub for impedance matching. Please note that the separation between the stubs D is fixed, and we find out the length of the stubs. Also, YL has been considered at the location of the first stub. In practice, YL will be the transformed value, that means a load impedance transformed by a section of transmission line to that location. Another point we should remember, we have shown a shaded region, and what we notice that if YL lies within this shaded region and if we follow a constant G circle, we cannot have a intersection with rotated G equal to 1 circle. That means, for the given arrangement of the stubs, we cannot find a solution for this range of YL. Please note that this region for which solution is not possible, the forbidden region, it changes depending upon the orientation of this rotated circle. For example, if D is less than lambda by 8 as shown here, then this circle will shrink, whereas if it is more than lambda by 8, this circle will actually increase in size. So, this actually shows the forbiddance range of load admittances that cannot be matched with the given double stub tuner, for which we have drawn the rotated G is equal to 1 circle. Let us now move on to another type of impedance matching network, which is called a quarter wave transformer. So, a quarter wave transformer, it is essentially a transmission line section of length lambda by 4, and it is having a characteristic impedance of Z1, and it is used to match a real load RL to a transmission line of characteristic impedance Z0. And we show this arrangement in the figure. So, here we have the characteristic impedance Z0 for the transmission line, and our ZL is equal to RL and here in between we have a quarter wave transformer having a length L equal to lambda by 4 and its characteristic impedance is Z1. So, what we can do? We can find out the input impedance looking at this point, and this can be written as Zin is equal to Z1 RL plus JZ1 tan beta L divided by Z1 plus JRL tan beta L. Now, what we can do? We can divide numerator and denominator by tan beta L, and we see that when L becomes lambda by 4, beta L tends to pi by 2, and therefore, we are left with Z1 into JZ1 divided by JRL, that means Z1 square by RL, and equating this Zin to Z0, we get Z1 to be equal to under root RL into Z0. So, what we find that a quarter wave transformer can match a real load RL to Z0 provided we select Z1 to be equal to under root RL Z0. So, we note that matching is obtained at the frequency at which the transformer is quarter wave long. So, this is very important to note, because once we have a physical section of a transmission line, this will be quarter wave long only at a particular frequency. So, exact matching is obtained only at a particular frequency, and also at all odd harmonic where the length corresponds to 2n plus 1 lambda by 4, that means 3 lambda by 4, 5 lambda by 4, for all these lengths also we will get exact matching. Now, as I have told that the length of the quarter wave transformer is exactly lambda by 4 only at the operating frequency f0. At other frequencies f greater than f0 or less than f0, this length will not be exactly lambda by 4, and there will be some amount of mismatch, and we can calculate the fractional bandwidth which is defined by delta f by f0. F0 is the operating center frequency and delta f gives the frequency deviation from f0. This can be found out, and this is given by this expression 2 minus 4 by pi cos inverse gamma m. Here this gamma m is the maximum value of the reflection coefficient that we are ready to accept, and depending upon this gamma m, the fractional bandwidth is given by delta f divided by f0. F0 is the center frequency or the design frequency, delta f is the frequency deviation, and this is given by 2 minus 4 by pi cos inverse of 2 gamma m. Gamma m is the magnitude of the reflection coefficient that we are ready to accept. You can see that with different value of acceptable level of reflection coefficient, fractional bandwidth will be different. So, this is cos inverse 2 gamma m divided by under root 1 minus gamma m square into 2 under root z1 into RL divided by mod of RL minus Z0. So, this expression will give the fractional bandwidth for the quarter wave transformer, and we can actually have different fractional bandwidth depending upon the maximum value of the reflection coefficient at the passband edges that we are ready to accept. Now, quarter wave transformer can also be used with other circuitry in the design of a matching network for matching a complex load impedance to a transmission line. So, we show some example of such networks. For example, here ZL is a complex load to be matched to Z0. What we can do? We can take a transmission line section of length D and transform this ZL in such a way that the imaginary part becomes 0. So, once we can do that, here we will be left with a real transformed value of the load, and that real value can be matched to the transmission line using a quarter wave transformer. Another example is shown here, where suppose we put a stub at the location of the load ZL to cancel out the reactive part. Now, it is shown with a shunt stub. That means, this shunt stub and ZL combined will give a resistive load impedance here, which can be transformed to Z0 by using this quarter wave transformer. Let us now move on to another topic, which is the theory of small reflections. So, here what we are considering? We are considering a load impedance ZL, a transmission line of characteristic impedance Z1, and in between we have another section of a transmission line with characteristic impedance Z2, and the electrical length of this section is beta L is equal to theta. So, this is essentially a single section transformer, and we define the partial reflection and transmission coefficient. So, here gamma is the overall reflection coefficient. Now, at this junction, when the wave travels, it sees a mismatch of impedance, and the partial reflection coefficient gamma 1 is dependent upon this mismatch Z2 minus Z1 divided by Z1 plus Z2, as we will see. So, the wave travelling in this transmission line, seeing a characteristic impedance Z1, finds a mismatch here, and gamma 1 is the partial reflection coefficient. Similarly, a part of the wave will also travel to the second section of the transmission line, and we have T21 is the transmission coefficient from transmission line section 1 to 2. Now, this wave travelling in this second section finds another mismatch when it reaches the load impedance ZL. So, we define gamma 3 as the partial reflection coefficient, and gamma 3 will depend only on Z2 and ZL. Similarly, the reflected wave from the load it will also get reflected by this interface, and this is denoted by gamma 2, which will again depend on Z2 and Z1. So, we can write this partial reflection coefficients. Gamma 1 is Z2 minus Z1 divided by Z2 plus Z1. Gamma 2 will be Z1 minus Z2 divided by Z1 plus Z2, which is same as minus of gamma 1, and gamma 3 will be ZL minus Z2 divided by ZL plus Z2. So, having defined gamma 1, gamma 2 and gamma 3, now we define T21, which is equal to 1 plus gamma 1, and it becomes 2 Z2 by Z1 plus Z2. Similarly, T12, which is 1 plus gamma 2, it becomes 2 Z1 divided by Z1 plus Z2. Now, let us consider here, suppose a wave of unity magnitude, it is incident here. Then as it first time reaches this interface, we will have gamma 1 as the reflected wave and T21 is the transmitted one. Then it will travel down this transmission line. So, the phase change is represented by e to the power minus j theta, where theta is actually beta L, and then it gets reflected from this point where there is a mismatch between the transmission line and the load impedance. So, it will essentially get multiplied by gamma 3 here. So, if we start with the wave incident here, we can see that here we will get T21, at this stage it will be T21 e to the power minus j theta, and then multiplied by gamma 3, then it will travel down. So, it will become T21 gamma 3 e to the power minus j 2 theta, and then at this interface it will get reflected again, and we have gamma 2 as the partial reflection coefficient, and T12 will be the transmission coefficient here. So, finally, the wave that will emerge from here will be T21 e to the power minus j 2 theta into gamma 3 into T12. So, these are all waves, reflected waves from this interface, and these are all partial reflected waves. So, we can write the total reflection coefficient gamma in terms of these partial reflected signals. So, we can write gamma is equal to gamma 1, the first one, then T21 e to the power minus j theta, gamma 3 e to the power minus j theta, T12. That means, this term becomes T12 T21 gamma 3 e to the power minus j 2 theta. Similarly, from here the partial reflected term is T12 T21 gamma 3 square, because now it will undergo another reflection here, and another gamma 2 will come here, because this signal is the reflected from here. So, we will have T 12, T 21, gamma 3 square, gamma 2, and total phase shift will be 1, 2, 3, 4. So, e to the power minus j 4 theta. Now, it can be, this term will be a common term in all the terms, and this can be put in a summation form as shown. It may be noted that since gamma 2, gamma 3, their reflection coefficient, their magnitude is less than 1, and we know that when we have a sum of x raised to the power n, where magnitude of x is less than 1, it can be expressed as sum of x to the power n, n tending to 0 to infinity, is equal to 1 by 1 minus x when mod of x is less than 1. And if we apply this relation, we can write this summation replaced by 1 minus gamma 2 gamma 3 e to the power minus j 2 theta, and hence we get gamma to be equal to gamma 1 plus T 12 T 21 gamma 3 e to the power minus j 2 theta divided by 1 minus gamma 2 gamma 3 e to the power minus j 2 theta. Now, we use the relation gamma 2 is equal to minus gamma 1, T 21 is equal to 1 plus gamma 1, and T 12 is equal to 1 plus gamma 2, which is equal to 1 minus gamma 1, and then we can write this expression as by replacing T 12 and T 21 and also replacing gamma 2 by minus gamma 1, we can put it in this form. Now, finally, it becomes gamma 1 plus 1 minus gamma 1 square gamma 3 e to the power minus j 2 theta divided by 1 plus gamma 1 gamma 3 e to the power minus j 2 theta. So, this we can write once we multiply this denominator term by gamma 1, and then the terms shown in red, they will cancel out and we will be left with gamma is equal to gamma 1 plus gamma 3 e to the power minus j 2 theta divided by 1 plus gamma 1 gamma 3 e to the power minus j 2 theta. Now, suppose we have the condition that discontinuity between Z1 and Z2 and Z2 and ZL, these are small, so that both gamma 1 and gamma 3, they are very small, and their product, magnitude of the product of gamma 1 and gamma 3 will be very, very small compared to 1, and neglecting this term, we can write, we neglect this with respect to 1 and we write gamma is equal to gamma 1 plus gamma 3 e to the power minus j 2 theta. So, it may be noted that e to the power minus j 2 theta is the phase delay when the incident wave travels up and down, and the total reflection coefficient is dependent on the initial reflection coefficient between Z1 and Z2 and on the first reflection between Z2 and ZL.